Today's lesson is over section 6.1, where we'll talk about more about areas. First, we'll start with a warm-up problem. So we've talked about finding the area under a region for just one function, but what about two functions? So first, let's take a look at the graph. So if I graphed y equals x squared, that's just a simple parabola, and then y equals 2x minus x squared. I looked for the x-intercepts here, which are 0 and 2, and then I tried to figure out where that asymptote is, which is halfway in between. So I found that it was 1 at the value of 1, and so notice that there's a little area in between the two that is like enclosed by those two variable or those two functions. And so here, if I want to find what the area is in between it, I need to have a range or from one x to another x, so that area is enclosed from 0 to 1. And looking at it, 2x minus x squared is actually above that function of x squared. So I would naturally want to subtract the 2 because x squared would be below it, and so would 2x minus x squared would be below it, but subtracting them allows me to get the area in between. And so using that integral, I'm able to kind of combine the two functions, factor out a 2, take the antiderivative of them, which is x squared over 2 minus x cubed over 3. And then using my FTC part 2, I'm able to find that the area is actually 1/3. Okay, and so that's kind of what we're going to start doing, is kind of looking at the area for a region bounded by more than one curve. And so this could be two curves plus some lines, which are going to either be maybe stopped by the y-axis or the x-axis, or two different values. We're going to have like a different area that we look at. So we actually subtract one from the other, and so how we kind of work at it or find it is to have the top function be the first one that we take, because it's always going to be the bigger one, right? And then subtract it from the smaller one, which is the lower one. So f of x will be the top, g of x will be the bottom. So here we need to kind of figure out what our intersections are. And so you can graph that and figure it out, but sometimes it's just easier to just set them both equal to each other and solve for our variable, which is x. And so here I set x plus 2 and 1 plus or minus the square root of 5 minus x equal to one another. Notice that it's plus or minus, so if I did these two separately, because I have to square both sides, the plus or minus actually gets canceled out, because positive is going to stay positive, a negative is going to change to a positive. So they actually become the same function. So I can actually do them at the same time. Then I'm able to find that x is equal to -4 and 1, and then I plug those back in to one of the functions to find what those y values are, so I can get those ordered pairs. And so now, going to the graph, I'm able to plot those a little easier, and then I can kind of sketch the parabolas or the functions that I have to kind of see what that area looks like and kind of how to tackle this. Now, you can always do this with x in mind, but if you look at this one, it's kind of slanted to the side because of that square root of 5 minus x. And so the line of x plus 2 is not always above that function of 1 plus or minus the square root of 5 minus x. But if you turn it sideways and looked at it from x, like the top of x axis, the positive x axis being the top, it actually looks like 1 plus or minus square root of 5 minus x is actually on top. So you can actually rewrite your functions into the other variable to help you kind of solve it using the other variable, which sometimes kind of helps make it a lot easier. So in this case, I solved both of the equations for x, and then from there, now I can see that, oh, negative y squared plus 2y plus 4 is on top, is bigger, because it's to the right, it's more positive than y minus 2. And so I subtracted those two, got a simpler function, and then took the antiderivative, and then proceeded to plug in those values of -2 to 3. So notice also, instead of using the x values of -4 and 1, because I switched to y, I'm using the y values because negative 2 is the smallest, so that's our A. And then 3 is our biggest, because that is our B. And so from there, simplifying all my stuff, I'm able to find that I get negative 70 divided by 6 plus 50. I'm put them all into terms of or same denominator with 6. You could have just plugged it all into the calculator. I believe you get 20.83 repeating, or 125 divided by 6. Either way, it doesn't matter how you write those. Now here I tried to do the same thing with letter B. And so ln of x, we need to get that x out of there, so I kind of changed it to exponential form. But notice that I still have an x up in the numerator, or in the exponent, so I can't really solve this normally. So here I'm going to use my graphing calculator to find the intersections, which is okay to do. Remember to do that. You graph both the functions, and then once you're looking at the graph, you go to second calculate, and then you look for the intersection one, and then kind of take a guess right where you think an intersection is. I was able to find that there's two intersections, one at 1, 0, and one at approximately 3.501 and 1.253. And so there's my region. Here, this one's a little easier to keep it exactly how they are, because ln of x is definitely over x minus 2 squared minus 1. And so here, I subtract the 2. Now these ones, they don't simplify like the other ones do, because ln of x is not any like terms with x minus 2 squared minus 1. So I simplified it out as best as I could. Also, trying to remember what the antiderivative of ln of x is a little hard, a little difficult there. So what I chose to do with this one, we did it in a previous lesson in the last unit, but if you can't remember, you can always separate it out and make it its own integral. So that's what I chose to do, just to re-show you how you can do this, because sometimes you're going to need to do this, so I thought it would be beneficial for us. So I made it into two integrals, ln of x by itself, and then negative x squared plus 4x minus 3 is together. And so then I use integration by parts. And so I set u equal to ln of x, took the derivative, dv is equal to dx, and then I proceeded to find what that would be. So x times ln of x for that definite integral. Remember that x times 1 over x, those will cancel out, giving me 1. So the antiderivative of that will be x. I took the antiderivative of negative x squared plus 4x minus 3. Notice that I've got several things going on all at once, and kind of keep the ball rolling here. So then I plug in the 3.501 and 1 into the x times ln of x. The antiderivative of 1 would be x, so I'm ready to do that definite integral. And then I do the same thing for the last function. And sorry, I kind of ran out of room, so I kind of moved it down a little bit. Now, because all this is just decimals, I start plugging them into my calculator. So the first part is just 4.3869, and then I am able to get 3.501 minus 1 in that parentheses there. In red is all that plugged into the calculator, and blue is all that plugged into a calculator. And then plugging it all into the calculator gives me the value of 2.926, and that's my answer. Okay, have fun.